Lab, we'll meet down here at 2:30. We'll have some lecture time, just like yesterday. Bromination of trained steel beam. Seemed to go pretty well yesterday, yeah. Recrystallization worksheet due tomorrow here in class. Yep. Bromination report. That will be due on, we have test on Monday. Okay. I'll just make the bromination report due on Tuesday, Wednesday. But that's off sequence. So we have to turn that in class. Okay. Monday lab, we'll turn it in Tuesday in class. Tuesday lab, we'll turn it in Wednesday in class. Yeah? That's for the bromination report. Bromination does have the stereochemistry in it, yeah? And we're kind of working some of that like right here. Now the bromination lab, the products are actually shown like this. The new things are forward and back. I'm actually recommending here in class to put the new things in the plane. Okay? So note that. But it is typical to also see it like that. You may see it either way. It just happens to be forward or back there. For doing problems, I recommend putting new things in the plane. That's what we did here, yeah? How do we have this here? We have the, which carbon is the chlorine on, or iodine? Which halogen is on the left carbon? Yeah, it'd be chlorine. And did we have one of them that was straight up? And one of them straight down? Yeah, because it's an anti-addition. What if we were adding H2 to this alkene? How does H2 add? Syn, because it comes from the metal, the same side, yeah? This is an anti-addition because it's an iodonium ion and chlorine does backside attack. Opposite side attack. Here we had, well, we can do them both, I reckon. We had two on the board. One of these is going to be 4 isopropyl group, and put the methyl back. And over here, put the isopropyl back. Is that one product there? Yeah? And the other should have been same way. That is, we have the methyl back and the isopropyl forward. And this isopropyl forward. No. Everything's the same. Those are all the same. The difference is, because the original alkene was here, but the pi bond's now gone, and these two things have added across the pi bond. But in this case, the chlorine's down and the iodine's up. Is that right? This is the two ways that the ICL can add to the pi bond. It's regioselective. The chlorine is on the more substituted carbon. But the addition can take place from either side of the pi bond. Did we show the iodonium ions? I mean, this originally was back bonded, okay? Did we get to look at someone's notes from yesterday? I don't see an iodine. Oh, there it is. You're missing an arrow. Missing arrows. Does everybody know how we got here? Show the iodonium ion. Everybody can get there? I'm not convinced, but I'll continue on. Okay. Next, need to be able to show Fischer projections. Can you show these are it. Is it erythro or 3O? That's the question. Is it erythro or 3O? Or is it both? What have we got? Isn't that one of the questions? What is the question? Is the product chiral? You want to clarify that question? Product chiral? Okay. Who says the product's chiral? Okay. Who says it's not chiral? I saw about 20% voting. All right. I'm going to continue on, guys. If you don't talk to me, I don't know what you need. Okay, let's do a Fischer projection. We'll do Fischer here. Does it give any instructions for doing Fischer?
Isopropyl groups at the top and bottom.
Isopropyl groups at the top and bottom. So either side can be bottom because we've got isopropyl groups on both chiral carbons here. I'll make this the floor for this one. I can stand here. Okay. We're doing the first one. Okay. With the chlorine going away, because it's in the plane, it's easy, I can look at it with it going away. With the chlorine going away, what side is the isopropyl on? This isopropyl. With the chlorine going away, the isopropyl is on. Chlorine going away, isopropyl is on. Chlorine going away, isopropyl is on the right, correct? And what's on the left if the chlorine is going away? Methyl group. I'll clarify that with an ME there. CH3, methyl, yeah? Everybody can get that right there. Isopropyl's on the right. Chlorine going away, isopropyl's on the right. Everybody good?
You draw where you're standing.
Okay. First off, I'm standing on the ground. I'm looking at this with the chlorine going away. So how do you want to stand? Well, for chlorine to be going away from me compared to that carbon, I'm over here, right? I'm also on the ground. I'm looking through here. It's like I'm laying right here on the sofa. Chlorine's going away. And if the chlorine's going away, what side is the isopropyl on? It's bolded, so it's coming towards you guys. If I'm over here, laying like this, it's on my right. Chlorine going away, isopropyl on the right. Is that what I drew? Yes. Okay, what side is the methyl on? Well, it's going behind the board. If I'm over here, it's going behind the board, like my left arm here. It's on my left. That's it. Okay, if the iodine is going away, what side is the isopropyl on? That isopropyl. With the iodine going away, the isopropyl is also on the right. The other isopropyl, correct? Everybody agree? Right? Gotta be standing up here, looking this way. Ground. Feet on the ground. The ground is that way. I'm up here. Why am I up here? Because the iodine is going away from me. What side is the isopropyl on?
Right.
Right. What's on the left? Undrawn hydrogen. Okay. There's compound A, this is B, this is A in a Fischer. But it says with isopropyls at top and bottom, right? We can just rotate this up, we can rotate that down. The isopropyl at the bottom, that's going to move the iodine here, the H over here. That's an iodine, that's an H. Isopropyl at the top. That's going to move chlorine here and methyl here. Everybody agree? Did we rotate those right? These three can just be turned like a clock dial. Those three can be turned like a clock dial. There it is. This is A in a Fischer with isopropyl at top and bottom. Is it erythro or 3O? Chlorine is high priority on this carbon. What's high priority here? Iodine. It is rethrow. Is this compound chiral? It's got two chiral carbons. Is it chiral as a whole? No plane of symmetry. Do you see your plane of symmetry? You can trust the Fischer projection. It's easy to see planes of symmetry. It's either straight through there. Is that a plane of symmetry right through here? No, you got to have a chlorine and iodine over here. About right through here. No, you got to have you got to have chlorine chlorines. There's no plane of symmetry. That's the only place you have to look. It's easy to see here. You're not missing anything. It's easy. Now, if you just look here, you could miss it because here it may be rotated wrong or something. You can miss it over here. Much easier to get it right in the Fischer projection. A is a rethrow. What is B? What will B be? A rethrow of 3O. B will be what? I didn't hear. A rethrow? Why will B be a rethrow? Like that.
Because the monomers are both urethro, or they're both rheo.
Okay. Yeah, the mirror image of a rethrow is a rethrow. I'm out of room, I'll have to erase. I'm going to erase A, I reckon. Or I'll try to do it over here. B, if we do it in a Fischer projection, would look like, I'm just going to go ahead and draw the end here. It would be, it would be that right there. What do A and B look like? Do the Fischers look like mirror images? You see how A and B look like mirror images? Yeah, they're mirror images. These are enantiomers. It's not chiral. There's no plane of symmetry. The mirror image is going to be different. That's just golden rule. If it doesn't have plane of symmetry, the mirror image is going to be different. Now we can make models of both of these and try to superimpose them. They will never superimpose. It's like your hands will never superimpose. Can I stack them on each other? No. If I stack them, I got a thumb on one side and thumb on the other. Now, I can do that, but that's not superimposing them. Superimposing is taking them just this and just, like if this one was a hologram. I need a thumb over here. Basically, the only way I'm going to superimpose, I need another right hand to superimpose on top of this right hand. The right and left will not superimpose. These two compounds will not superimpose. Okay. Is the reaction regioselective? Yes. By the way, is it stereoselective? Well, that's a broad term. Let's get more specific. Is it enantioselective? Not enantioselective. We got both enantiomers. And we've already said that none of the reactions we're doing are enantioselective. Is it diastereoselective? Is this reaction diastereoselective? No? Why not? So when it had we had a choice of diastereomers and you saying it did not choose one over the other? What type of diastereomers are theoretically possible for this type of compound? Erythro and 3O. Okay, did we get both erythro and 3O? No, we only got erythro. So was it diastereoselective? Yes, it was diastereoselective. We only got Is it stereoselective? It depends. It's yes and no, depending on, you gotta get more specific than just, is it stereoselective? So if someone asks you if this reaction is stereoselective, you gotta say, are you talking about an antioselective or diastereoselective? Gotta get more specific than that. Okay. Any last questions about that? Everybody good to go on all that? All right, so that's stereochemistry. Let's move back to Alkyne. Any questions about hydration of alkynes, tautomerization, tautomers, etc.? Are you guys okay today? You don't seem to be with it. What's going on? Something going on? Okay, I'll plow ahead. Hydration of alkynes. On the previous page, we hydrated with basically aqueous acid, but you can include mercury ion there. Okay? It is a better catalyst. Mechanism may be a little bit different. Mercury is going to back bond. It may keep it from rearranging. You may get better yields because it doesn't rearrange. But in the end, just ignore mercury. We're going to just do it without the mercury and just use H+ catalyst. Okay? Now, we know and with alkenes, you can oxymercurate, and it's a specific reaction. You can also do hydration by hydroboration oxidation, and you can do that with alkynes as well. So, we can get the enol here with the OH on the N carbon, because if this attacks the boron, the electron poor boron, where are we going to make cation at if we do that type of thinking? Cation on left or right? Cation on left, so this swings away and attacks the boron, and wouldn't we get boom, 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 double bond, but that swung out and attacked the boron, right? And left that as a plus. And the boron is now a minus. Now this is not actually formed. Well, in many ways, some people don't even like to show these so-called vinyl cations. I'm doing that, but again, is this actually formed? The way I've been presenting these pi bond reactions. What happens here? And let's do a hydride shift. These electrons, okay, I'm seeing people do this. Some of you are doing this kind of mechanism. What does that arrow mean? I don't know what that means. It looks like an H is moving here. Arrows don't show movement of atoms. I also saw some mechanisms kind of like this, for arrows. I don't know what that means. Does that mean a charge is moving over there? I don't. Arrows mean something precisely, okay? Understanding arrows and using them as part of organic chemistry. What happens next? The two electrons, every time you move an arrow, these electrons, right? These two electrons break away from the boron. The arrow is like you grabbing the electrons. Let's grab the electrons and pull them over here. Now the H is going to come too. The H is connected to the electrons. We didn't disconnect them. We're not saying we're disconnecting electrons from the H nucleus. We're disconnecting them from the boron nucleus, yanking them over here, but the H is connected, right? Precise arrow movement. What does that give? Double bond here. This is now trigonoplanar. And the BH2 is like that. Make sure they condensed. But the new H is here. Now that's an alkene. Does everybody agree that the boron and the new H are going to be on the same side of the alkene? They're cis on the alkene. Why are they cis? Because the H came from the boron. It's a cen addition. Now there's also an H here. That was the original H. It's there. Okay? What does the magic step do? That's in step one. What does the magic step do? Yes, you can just mark that out and put an OH there. I'm going to erase it. It replaces it with OH. Magic. And what is that there? Well, that's the enol. That's what's shown above. The step shown above, I just don't have the H shown. Right? But what do we know about enols? They're unstable, right? They undergo a process called tautomerization. That's just a rearrangement where we relocate a single H. Okay? What's the product going to look like? Uh-huh.
So when you say earlier, some point you said tautomerization is not a mechanism, were you just saying we can't just write tautomerization, we have to show it, is that what you meant?
Well, I think I understand you. Tautomerization, there is a mechanism through tautomerization. But if asked for what the mechanism is, you don't just write tautomerization. Just like when we hydrate an alkene and I asked you, okay, show the mechanism, you wouldn't just say hydration. That's just a descriptor. Okay. What is the tautomerization mechanism? You need to know that. But here we just, what is the product? When this thing is going to tautomerize, what's going to be the product? The most common tautomer of an enol is what? The double bond relocates to where? Between the C and the O instead of between the C and the C. It becomes a carbonyl. Enols, the most common tautomer of an enol is the carbonyl form. Previous reaction, it was a ketone, right, on the previous page? What is this product going to be? Anybody got the structure? What's the product? Yeah, that's it. Anybody else got the structure here? Actually, can you show a carbonyl compound instead of that? Carbonyl would be a C double bond O. You want to put the double bond here. 1, 2, 3, 4, 5. Double bond here instead of there. Now, this is probably going to, that's it right there, yeah? We can talk about that, yeah. The double bond ends up here, and we relocate this H. That H is gone from the oxygen, right? Where's this H at now? On this carbon now, there's 2 here now. Here's what will confuse you if you don't think. It's like, how did that H move from there to there? It did not. That's not the same H. That H is still there. It's still here. There's actually 2 there now because that one and that one are both there. This is just the H of the aldehyde, which I've told you before. Haven't we said that before? I prefer to draw in the H of the aldehyde than most chemists do, even though it's on a carbon. It looks a little naked without it. Okay? Product of this reaction is not the enol, it's not stable. It rearranges by tautomerization to, in this case, an aldehyde. Julia?
Yeah, does the H that gets transferred, does a water take it, or does it move into the molecule itself?
Well, we did mechanism yesterday. Do you have the mechanism?
I didn't know if it was the same.
No, but also I said yesterday, we gave a mnemonic for the mechanism Oreo.
Yeah.
And I told you the Oreo mechanism works with any tautomerization mechanism. The only thing is, if you're under acidic conditions, the first O stands for what? On. If you're under basic conditions, the first O stands for off. What type of conditions are we under here? Well, we're under the second. Because after the first reaction, we don't have the enol. You don't have the enol until after the second reaction. But as soon as it's formed, we're still under these conditions. So we're under acidic or basic? Basic conditions, yes. You want to show mechanism for this? Why don't you show mechanism for that reaction right here? What is the mechanism? Again, the mechanism is not tautomerization. That's just a description.
Kind of confuses when you draw that picture together, because it makes it look like hydrogen's been put oxygen to there, but that hydrogen's been there the whole time.
Well, that's what I said. I said if you don't think, you're going to think that this is that H.
So why don't we draw the 2 hydrogens where it's actually going instead of going?
Because the product is an aldehyde, and that's how you would typically always see the product shown right there. But I warned you, and I explained to you that the H that's being moved That, everybody agree that that H is being moved because it's no longer here. Where is that H now? It's on this carbon, because that carbon only has one there, there's two here. So at this point, I expect you all to figure all that out and make sure it's clear in your mind. And that means that you got to be able to do that. I mean, you want to erase that H, you can. Mechanism? But we're under basic conditions. You did it as if we were under acidic conditions. Basic conditions. All this is happening in reaction 2. And reaction 2 is basic conditions.
Can you draw the mechanism?
We'll do it. Well, the first thing I'm going to do is, because I'm going to remove this H. Now, if it was on your paper, you can't erase. But let's do this. Let's get rid of that and draw that bond out. We need a bond if we're going to do a mechanism. We can't work with condensed structures. Now, this was clearly stated on the mechanism page I gave you. And the first step is what? H off. What H do you want to take off? The one that needs to be removed. Which one needs to be removed? That one. What do you want to take it off with? Hydroxide, the base. These electrons take the bond to the H. These stay behind. That's going to give O. How many lone pairs on the oxygen now? There's 2. 3 in charge?
Negative.
Yes, negative. So we just did H off, proton off. You can actually call it H plus off because we treated that as an H plus. We didn't take the electrons, just the H nucleus. The H nucleus is positive. Okay, what do you want to do next after we took the proton off? Julia?
Resonance.
Resonance? Okay, we've not done resonance like this. We'll start doing it tomorrow. We're going to call this the old in and out resonance. And that is using on the paper here on our board. These electrons can move here, but that carbon can't have 5 bonds. There's an H here, right? Okay. So what we're going to do is we're going to move these pi electrons here. And what does that electron movement give? What do we now have between the C and the O?
Double bond.
A double bond, yes. How many lone pairs on the oxygen? 2, because one of them moved in to make pi bond. Okay? We never move a lone pair from here and put a lone pair here. That's not what that arrow means. We will never ever do that. This means the lone pair is moving in to make another bond. It is a pi bond. Okay? What does this arrow mean? These pi electrons, we're doing what? We're moving them out here to become what? They're moving out here to become a lone pair. Now, one thing we'll say starting tomorrow is all resonance structures should have the same net charge. That is net minus. This has to be net minus. Where's the minus? That carbon is now minus. How many H's on that carbon right here? 1. There's 1. If you look at that, it's a minus charge. Charges need to be shown right next to the atom. Some of you on quizzes or last tests showing charges sort of just over here or something. It should be right there. right there. So this was resonance. Because this is just another Lewis structure of the same compound where all we have moved is pi electrons. Whenever you do resonance, you never move atoms. Did we move any atoms when we went from here to here? No, we only moved electrons, and specifically pi electrons. We'll do more starting tomorrow. What do you want to do next, Julia? Proton on. Where do you want to put it on? Well, where does it need to be on? I mean, if you already know the structure, you know it needs to be here. Or you can say, okay, this needs to go neutral. How can it go neutral? You can take a proton from what? Well, up here we made this plus what? Plus water. Well, this can now take an H back from water. These electrons bond to H. These electrons move here. And that gives what? Well, that gives your final product. And now there's two H's here, and it's neutral. What did we also form, though, in this reaction method step? We formed OH minus. So in terms of this tautomerization mechanism, we started with OH minus. It did something. We regenerated it. What is OH minus? Yes. This is a tautomerization catalyzed by base. Yesterday, previous page, we did tautomerization catalyzed by acid. And yes, at this point, this is an aldehyde. I didn't draw the H in there. I did at the end, again, because most times aldehydes are drawn with the H. Oreo, did Oreo work? Oreo will work with any tautomerization mechanism. Today, any compound. Question?
So if we drew that without the H as like our final product, would that not be correct?
I could not count off. I mean, I'm just recommending that it's usually going to be drawn with the H. Aldehydes are typically drawn with the H only. In this case, it is an aldehyde. Yeah? Previous case, it was a ketone. That's because in the previous case, there was no H here instead of an R group, so it was a ketone. But that's irrelevant. I mean, same mechanism. I see something we didn't do. And I don't think I did this on nomenclature video. Back here at the very beginning. Nomenclature of alkynes. Let's look at that. Question I was going to ask is, what type of alkyne did we just hydrate in that reaction we looked at there for 20 minutes? What type? Terminal alkyne? We haven't covered that yet. We had to do know the terminal.
It's on the end.
How did we know?
Program.
Where?
At the very beginning.
On that page over there?
Yeah.
Oh, when terminal alkyne is used, okay. Well, what's a terminal alkyne? Yes. Terminal alkyne is where it's at the end of the chain, and thus the last carbon, the carbon on the end, is bonded to an H. It's called a terminal alkyne. If the alkyne is sort of in the middle, not on the end, and the two alkyne carbons are bonded to carbons and no H, that's called an internal or non-terminal. Okay, but that's the difference. And the kind we just hydrated was a terminal alkyne. On Monday and Tuesday, we're doing hydration of an alkyne, one hexyne, but we're not hydrating with borane, we're hydrating with aqueous acid. We're not using any mercury, although in textbook, mercury is often included. But it's not absolutely necessary. Mercury may give better yields. The yield on Monday, Tuesday might be a little low. But that's fine. We're not going to use mercury and contaminate the environment or whatnot. Because then you have to dispose of it. Expensive to dispose of. You have to do that properly, etc. And that lab on Monday, Tuesday is a group lab. Okay? We'll do that in groups. And the report is a group report. Okay? So that's coming Monday, Tuesday. Nomenclature. Let's name this here. It's just like alkene nomenclature. All nomenclature is pretty consistent, pretty similar. Longest continuous carbon chain. Well, it's 1, 2, 3, 4, 5. It's 5 carbons, yeah? It's just, that's only one chain. So it's pent something. Well, if it was just saturated, it'd be pentane. If it was an alkene, it'd be pentene. But here we see an alkyne, so it's called pentyne. All right? The suffix there indicates what type of functional group. Now, just like with alkenes, you indicate where is the double bond or triple bond. Well, and it takes precedence. Well, there's no other substituent here. You want that to be 1 or that to be 1? That to be 1, and you call this 1 pentyne because that's where the triple bond is. Just like alkenes, it's at the 1, 2 position, but we only list the first number. So that molecule is 1 pentyne. What would you call the next compound?
3 heptine.
Micah? 3 heptine. Anybody else? You agree? 3 heptine? Well, it's 1, 2, 3, 4, 5, 6, 7. That's the only chain there. You want the alkyne to be at the lowest number. Be over here, right? 1, 2, 3. The alkyne's at the 3, 4 position. We only list the 3. Yes, 3 heptine. The 3 indicating where the alkyne is in that chain, yeah? How about this? What if I put a chlorine here? And I'll give it some stereochemistry. What would the name of that compound be? You know 3 heptine was the original. Draw that on and let's give it a new name.
6
The name of this compound is 6 chloro, 3 peptide. I agree? I heard 2,4. Now, in alkenes, the alkene gets precedence. You label the alkene before you start. Okay? You don't treat it like just two substituents. The alkene takes precedence. And so we still want to be coming this way, so the alkene at the 3. If you come this way, it will give you a 2, 4, but that's giving chlorine precedence. The alkene and the alkyne take precedence, right? So it's still a 3 peptide. And then the chlorine's down to 6, 4, 5, 6. But is this name complete for that structure I showed you? What do we need to add to this name? We need to put an R here, correct? Because isn't that, we have the chlorine is on a chiral carbon. It's chiral, right? Thus it has 2 choices, 2 configurations possible. It could be RS. Which one is it? R. We could also have the S form, maybe a different compound and a different name. I mean, the S form would have the same exact name. Those stereoisomers have the same exact name. They just differ with some type of stereochemical descriptor. Look good? How many stereoisomers possible for this compound with the chlorine? Total stereoisomers possible. Libby?
2.
I thought someone said 4. No?
There's only 1 chiral carbon, right?
Yeah, what about the alkyne? Alkenes could be stereogenic. Alkenes could be cis or trans. Are alkynes stereogenic? Can we show 2 different forms of the alkyne? I can for an alkene. I can show the alkene with the cis configuration of groups or with a trans configuration. Cis or trans, isn't it? No, alkynes are not stereogenic because they're linear. They don't, no. It's linear. Alkynes are never stereogenic. Only alkenes have possible stereochemistry. Cis and trans. But not always, right? Sometimes, not all alkenes. You have to be able to identify when an alkene is stereogenic and when it's not. But alkynes, never. Yes, just 2. Everybody with me on that? Okay, so back over here we hydrated. Okay, reduction of alkynes. First we'll look at hydrogenation, like we hydrogenated alkenes using H2. Okay, first let's take a 2-minute break, and we'll finish up this handout.
trying to do Fischer projection and the Alkynes, the 6-chloro.
With the chlorine I added, Fischer projection?
Yeah,
Why do you want to draw a Fischer projection of that?
she just want to get it. I want to see the volume when it's on. There's actually
You don't, shouldn't need to. I mean, the H is in the back. Carbon has an undrawn H, it's going back. All you gotta do is 1, 2, 3, and then
okay.
if the low priority group is in the plane, then that's when I suggested Fischer, because you have to look at it a little bit differently. But if it's going back or forward, it's easy. If it's back, you just do it. If it's forward, you do it and then reverse. Got a little, something on the leg there. Let's see if it heals up, but she's also got a broken tail. Yeah, and apparently some nerve damage and affecting her bladder. So we'll see.
So they know what happened, or how they need to do it.
I don't know. She might have got hit by a car. Or just fell off of the deck or something. Kind of a high deck. I don't know. But okay, guys. Reduction of alkynes. The pi bond, carbon-carbon pi bond can be hydrogenated. H2, precious metal catalysts such as nickel, platinum, palladium. When we do one equivalent of H2, we're going to get the cis alkene. Right? And there's new H here and new H here. Why is it cis? Because the alkene is planar, and it approaches, and you're the metal, and what happens? Two H's are just sort of like this, same thing. Two H's, boom, two. Two H's. Okay? That's your fancy mechanism right there. It's not well known, but it is known to come from the same side. The two H's come from the metal. It's going to be cis. It's going to push these two methyls to the same side. And you end up with cis alkene. Well, guess what? Can alkenes react with hydrogen? Yeah. So it's going to react again. And when it reacts again, what do you end up with? No longer any pi bond. It's totally saturated. And 4 H's have been added. 2 equivalents. This reaction, it's hard to stop here. It's going to go all the way. Basically, this is going to react all the way with H2, 2 equivalents, and something like palladium or platinum or something. Okay? So it reacts twice the fun. And we went from the alkyne partially saturated it down to the alkene, and then it becomes fully saturated with another addition of H2. And when you add H's, it's called reduction, right? So we're reducing the alkyne all the way to the alkane. Now this reaction, you're like, wow. The more you know, you're going to, why would you do this? Because usually this is sort of comes from petroleum, and you work to incorporate double bonds. And we'll do that later. Why would you want to turn around and get rid of all your hard work and take it back to just a simple alkane? Well, there are reasons, cases, times when you might want to do that. It certainly can be done, and you need to know that it can be done. It's hydrogenation. I mean, a lot of maybe natural products are like this, like natural oils and like olive oil. Have lots of double bonds. And we saturate them to make the oils more stable. Those double bonds can be reacted with oxygen as well as other things. And we can make saturated fats, they're more stable, and now McDonald's can use the oil longer. They don't have to change their oil as often. They're using saturated fats, more stable. So there are times where you want to go from unsaturated and saturated, reduce it down. Okay, can you stop at the cis? You can. We'll look at that. Not with a regular catalyst. You have to use a special catalyst, and you can stop at the cis. That would be called partial hydrogenation to cis alkenes. If you use what's called a poison catalyst, it is a catalyst, usually precious metal, but something has been added to it to make it less active. A weaker catalyst. And it turns out that you can just do this reaction and stop here. And it won't keep going unless you can isolate a cis alkene. Up here you can't isolate it. That's what the brackets mean typically. We've seen brackets before. It ain't going to be, you can't isolate it. It's going to keep reacting. What are your examples of poison catalysts? The most common one is actually a name called Lindlar's catalyst. That's a pretty darn common name there. That's probably palladium mixed with some type of heavy metal salt. Like barium carbonate, lead sulfate. These heavy metal ions can absorb to the metal and make it less active here. Quinoline. If you look up Lindlar's, it may contain some quinoline. That's an amine. Amines can absorb to the metal and make it less reactive for the hydrogenation. Some type of poison catalyst, you may see it's shown as Lindlar's catalyst. Whenever you see that, that means you can stop here. And it actually will not continue. Typically will not. And so if you're using poison catalyst, that won't work. You have to use a non-poison catalyst to get it to go there. Alkenes cannot be reduced to the alkane if you use a poison catalyst. You have to use a regular catalyst. Yeah, questions? Pretty straightforward reaction. There's no regiochemistry. We're adding an H to each carbon. We know they're coming in cis or syn, same side. That's why it's a cis product, because the H's are on the same side. Question?
So if you wanted to unpoison, would you just add just a regular catalyst that's not poison, like a no catalyst?
Yeah, just like palladium carbon or nickel or something. That would be just a regular one. Use a regular catalyst, it's going to go all the way. We'll reduce all the way down to the alkane. Yeah.
When you're using the poison catalyst, why would it create the cis alkene? And like, why would it just not have it all? Like, it creates one product, we're going to create the second.
Why does it not keep going?
No, why does it create that one? Like, it doesn't create the alkane, but it creates the cis alkene. So, like, what's going on with its?
It's just not continuing.
Yeah, I know.
Are you asking why is it not continuing?
Like, why is it doing that one, and not just not having it
Oh,
all?
why does this work?
Yeah.
Why does this still work? That sort of implies that that this is easier than that. The easier one still works, the more difficult one does not. Why might this be easier? Well, we could look at the pi bond strengths, and we haven't really looked at that before, and I'm not really prepared to tell you. It may mean that when you have two pi bonds, that they're weaker pi bonds and they're more easily hydrogenated, and thus a poison catalyst will still do this, but over here it will not. All that sort of implies that this transition state is sort of more difficult than that. Yes, there has to be a reason why this still works, but then that doesn't work. To me, it implies that it's more difficult to reduce an alkene than it is to reduce an alkyne. The easier works, and then the more difficult one doesn't. But there's many other possible explanations. Because these reactions are known to be very finicky and very prone to many things. For example, it could be something as wild as maybe the alkene, for some reason, complexes with the metal salt and keeps it from further reacting, where the alkyne does not. It could be a million and one different explanations. These reactions have a lot of different finicky little variables and good question, hard to explain. But this is a way to make what? What type of compound can you make by hydrogenating an alkyne with a poison catalyst? Alkene, but what specifically? Cis-alkene. Okay? And as you go along, your toolbox of reactions will get bigger and bigger. We have, okay, for example, how do you make alcohol? More general, it's what are you doing? What's the starting material? Hydroboration of what type of compound? Alkene, right? Okay. In general, you're hydrating an alkene by hydroboration. So again, how do you make alcohols? You hydrate an alkene by a variety of methods, different regiochemistry. Okay. Do you know any other ways to make alcohols?
Hydronium.
H3O+.
Reacting with what? That would be a hydration of an alkene. Yeah. There's different ways to hydrate an alkene. What I'm asking is, do you know any other way, other than hydration of an alkene? Well, the answer at this point is no, you do not. But by the end of Organic 2, you'll know several ways to make alcohols. Okay? And these different reactions, transformations, are what I call the toolbox of reactions. Okay? Do you know how to make alkenes? We go the other way. So start with an alkene and hydrate it. Do you know how to make alkenes? Yeah, more specifically, by what conditions or by what? Well, not necessarily. I need more information. Poison. Because if it's not poison, you're not going to get an alkene, you're going to get an alkane. So do you know a way to make any alkenes? Yes, you now know how to make a cis alkene by that reaction right there. So this is organizing your knowledge. And in organic chemistry, making different types of compounds is a big part of your knowledge, and realizing that you know these things. All right? By the end of Organic 2, you will know many ways to make alkenes. All right, well, let's ask another question. Do you know how to make a transalkene? Not right now, but if we turn the page, we might. We can also partially reduce an alkyne to a transalkene, but not using hydrogen. Because anytime you use hydrogen, it comes from the same side, that's going to give cis. How can we get them trans? This is a neat reaction. It's actually our first radical reaction. Using sodium metal. What's the charge of the sodium here? Charge of the sodium? Charge of the sodium? No, it's not +1. If it was +1, I should have showed a plus. Charges are not shown, it's all destruction. If it was plus, what would be the minus? You can't have a plus without a minus. This is neutral sodium metal. Right? Any element can be met just in the atomic neutral form. You ever seen sodium metal? Did you use it in Gen Chem? You used to be in Gen Chem, you would demo it, cut it. Who said that? What you saw in Gen Chem?
Yeah, we used it in the lab. I think that was with batteries.
What did you react sodium metal with something?
No, we were using it as a cathode. We were doing a cathode and anode.
Okay, okay, because sodium will do redox. It's pretty strong redox action. It really wants to become sodium plus, and so it's a strong reducing agent. Yes. Quite strong, it will be very exothermic. Sodium metal, sometimes you can put a 0 at the top to indicate that the oxidation state is 0, and it's sodium metal. But you really don't need that. If you just see Na, right? Now if you show, what's the charge of that sodium? No, that's plus, and Cl minus. This is just sodium, it's sodium metal, okay? We might, if we have some time, we can cut some in lab, okay? It's pretty soft. Called a metal, but it's like hard, it's like Play-Doh kind of. Cut it with a knife. And ammonia, what is this? 1 pair, that's just a neutral nitrogen. Ammonia, yeah. Sodium and ammonia. Now this reaction is done at liquid ammonia, all right? Liquid. Ammonia is a gas at room temperature, but if you chill it down to -33 degrees, it will condense to a liquid. And you can actually use liquid ammonia as a solvent. And that's what's used here in this reaction. Because other solvents, more traditional solvents, would react or not work. Okay, the first thing is the sodium, put it in ammonia, fascinating reaction will take place, a little bit hard to explain. But the sodium will become sodium plus. But what did it have to lose or give up to become sodium plus? Yes. It will release an electron. Now, very often the electron, like in your cathode anode, the electron will be transferred to something else immediately. But that transfer will create electricity as the electron flows. Okay? And if you have enough, you can get a flow of electrons as the reaction will take place a million gazillion times. Okay? Where does this electron go? Well, it's said to be solvated. Okay? The only place it can go is to the ammonia, but the ammonia doesn't really want it. But it's solvated. And then, what does that mean? Solvated by ammonia. Well, it's almost probably maybe like hydrogen bonding. We got these H's here, right? Don't we show hydrogen bonding an H between electrons? It could be some type of just non-covalent interaction here, almost akin to hydrogen bonding. It's very fascinating. It's kind of a little bit vague of what's going on here. It's said to be solvated electrons. It's almost like they're floating in the ammonia. It's free electrons. You can read more about it. One thing is, when you put sodium in ammonia, it will turn brilliant blue. Okay? A royal blue. And a free electron is considered a radical. A lot of times radical reactions have deep purple or blue colors. Okay? Certainly something's going on. The colors indicate. Okay, the electrons. The electrons, they actually will pump into here. So it's pretty, you can almost consider the electron just going here. I'm going to consider the electron maybe as a dot or something, electron. And the electron pumps into the pi here. And we do this like this. When we move one electron, we use a half hook arrow. I'm thinking this is probably on the mechanism sheet I gave you with lots of tidbits. It's called a fish hook arrow. Okay? This is also different because all of our previous reactions, the pi bond attacks something. Here the electron is coming into the pi bond, and these electrons move over here. Now that's a pair moving. So I did a regular arrow there. What does that give? The pi bond moved over to this carbon, so what's over here now? A lone pair, right? What's over on this carbon? What just got pumped in? Single electron. Hold on. We should draw this to the other two groups. Each carbon also has a methyl. These methyls will be trans. Why will they be trans? It's as simple as it had a choice. And when it has a choice, is it going to prefer cis or trans? Trans. It could do either, but the transition state leading to trans is going to be lower because trans is more stable. Well, we're missing charge here. What is charged? What's the charge of this carbon? Neutral. What's the charge of that carbon? Minus, correct. Okay? What's the charge of an electron? Minus. If you add an electron to a neutral compound, what should be the charge of the compound then? Minus. It is. The compound's now minus. We added an electron to it. Seem reasonable? Does the arrow movement give what I showed? Also, just considering that it should be trans, because that's the best. Yes. Electron comes in and pushes the pi bond over there. Okay. What do we need to do here? Does everybody agree we need to add an H there and an H here? Because they're not there. At this point, this takes an H. What does it take an H from? Takes an H from ammonia. Is ammonia an acid? Who said no? Ammonia is not an acid? So, can this carbanion, that is a carbanion, right? Carbon anion. Can it not take an H from ammonia? It can? Why do you say it can?
Because it can be either an acid or a base, depending on,
Exactly, yeah. Be an acid or a base. Ammonia is usually a base, particularly if it's aqueous environment. But it can be an acid. And in this reaction, it's an acid. Because where else do the H's come from? You got two H's over here. They had to come from ammonia, right? These electrons take an H. These electrons move here. It's our good old acid-base mechanism. What does this give? We now have an H there. Plus what? What does the nitrogen now look like? How many lone pairs now of nitrogen? Two. And the charge? Negative. That's just a good old acid-base reaction that you should have been able to show 10 days ago. We're not done here. What did we lose? Yeah, that's still there. We need another electron here. Another electron can team up with that one. By the way, what do you call something with an unpaired electron? A radical. Sometimes called a free radical. Because it's like a free electron. It's not paired up with it's not a bonding pair and it's not a lone pair. It's a free radical. Back in the 1960s, free radical meant something else. All right?
Oh, that's what it means. Oh.
Look up 1960s. Woodstock, San Francisco. You'll read about free radicals. What does this give? By the way, where does the other electron come from? Because sodium, how many electrons can sodium supply? One. But we need two electrons. So how many sodiums do you think we need? Two. If we want to balance this, it requires two sodiums. Because you need two electrons. Here comes the other electron. And what does that give when you pump that in? We now have anion here, carbanion. Okay. There's neutral there. You can do a formal charge. One last step. What do we need to do here? We need another H. Where's the other H going to come from? From ammonia again. These electrons take an H, these electrons stay behind. What does that give? That gives final product plus what? Can I show that condensed instead of drawing out the full structure? What would it look like? NH2 minus? Yeah? NH2 minus? How many ammonias do we need in this reaction? We need two ammonias. Well, guess what? Now your reaction is balanced. I told you I'd never balance another reaction, but thought I'd do that one. You see? If we completely balance it over here, we get this. What else did we form here?
Another NH2.
I mean, if we write everything that was formed, we formed two NH2s. Now it's really completely balanced. Two sodiums over here, two sodiums over there, two nitrogens over here, two nitrogens over there. How many H's over here? 6. There's 6 H's over here. How many over here? 4. 6. There's 6 over there. I suspect some of you don't understand what this is. NaNH2, that is a salt. What's the charge of the sodium? Positive. We got 2 positives. Where did we form them at? Well, we did that twice, because it gave up 2 electrons. We formed 2 positive sodium. Look at this. What's the charge of that nitrogen? That should be super easy. That's no different from this. What's the charge of the sodium? Plus. What's the charge of that one? Minus. What's the charge of the plus? Positive. What's the charge of the nitrogen? Minus. NH2 minus, 2 of those. Did we form 2 of those? Yeah, there's one and there's the other. But see, the minuses can just be shown with the pluses. If I form Cl minus and sodium plus in the reaction, is it okay if I just say we form NaCl? That's all I did there. Because that's NaCl. Completely balanced reaction. You're okay. It's just trans because it had a choice. See, when you hydrogenate an alkyne, it doesn't have a choice. The H's come from that side. It has to be this. Here you have a choice, and that's why it's trans. This is called a partial reduction. It's also called a dissolving metal reduction because metals are not soluble. But as this reaction occurs, it becomes soluble because that's not soluble, but it all dissolves, and at the end it's all dissolved. And so your metal's dissolved at the end. And so it's a very generic term. It's the metal dissolved. Later we may use metals like iron or zinc or tin for nitro group reduction. We call that a dissolving metal reduction because the iron dissolves. Very general term. Okay, last topic here, acidity. Any questions up there? Yeah? It's a radical reaction.
So with every radical reaction, you're typically going to have 2 at least, because you're going to need 2 electrons.
Not necessarily, no. No. The common thing for a radical reaction is we have a single electron. We have something with an unpaired electron. We generate, in contrast to an ionic mechanism. Now there are ions on the board, but did the organic molecule ever, actually it did become an ion, didn't it? Yeah. Okay. So this is actually a mixture of radical and ion. Some mechanisms may be only ions, and that's all the ones we've done before. They were not radical, they were only ions, or neutral. This is both. Some mechanisms that may be only radical.
So it would stop.
Well, no, it'd be very different from this. It's just, you would never, the organic would never become an ion. In this case, you had both an ion and radical. Just stay tuned. Okay? But you can call mechanism ionic or radical. It's actually both. It's a blend. It should be just very straightforward. We see both radicals and ions on the board. Okay, Acidity of terminal alkynes. And probably know what a terminal alkyne is. Formation of what? Alkene. That term's not used much. Sometimes. Acetylide is sort of more common. What does the "ide" ending typically mean? Chloride. Specifically anion. Anion, right? Can we generate anions here? Carbanion? Terminal alkynes have slight acidity. The CH. And we actually mentioned this with the acid-base chemistry we saw, acid-base enzyme. And usually CHs are not that acidic at all. All right? Because usually you don't really want to make a carbanion minus on a carbon. It's not that electronegative, right? You'd rather make a minus on an oxygen or a bromine. That's why HBr is so acidic. But a terminal alkyne, that CH, has some acidity, and we can deprotonate it. The pK is about 25. Now we need to start running pKa's, yeah? What other pKa's do you know? Alcohol. 16?
Water, 16. Water, 16.
16?
Yes, water. And alcohol, 4.
Okay, terminal alkynes can be slightly acidic. pK about 25. But not that acidic. We need a pretty strong base. Common bases here, N-butyl lithium. N-butyl lithium is normal butyl with anion on the end, minus, and a lithium plus. It's a carbanion base. This carbanion will take the H, these electrons stay behind. What do you get? We now have lone pair on the alkyne carbon, and we created butane, right? This has just become butane. I just showed it as butane. This is basically one carbanion acting as a base to form another. Yeah? Which side's favored, 25 or 40? 40's favored, right? By how much? At least 10 to the 15, which is 100 billion or something. Will this reaction take place as shown fully? Yes. Okay. Why? Look at the stability of your two carbanions. Which one's more stable? This one is sp3. This one is what? sp. Much more stable, right? That's why the reaction is going that way, even though it's going from one carbanion to another. Another base you can use here is actually sodomid. In NH2, we actually generated it above. Right? Okay? This is Na plus, NH2 minus. That can actually act as a base here. These electrons take the H, these stay behind. We get this. By the way, the cation is going to sit with the minus. Down here we generate what right there? Ammonia. Ammonia is generated. pKa of 35. Which side's favored? 25 or 35? This side's favored. Both of these bases will deprotonate a terminal alkyne. What do we call the... We can call this a carbanion. We can call this maybe an alkyne carbanion. What other names can we call this? Alkynide. It's like an alkyne anion. Alkynide. More common though is acetylide. Acetylene is the most simplest alkyne. 2-carbon alkyne is called acetylene. Where do we use that at? It's used as a gas, acetylene gas for torches. Okay? The anion of that specifically we call it acetylide, but sometimes the term acetylide can be used for any alkyne anion. You don't see this term quite as much, but it should make sense. Okay? We can make acetylide anions by using such bases. Can we use hydroxide as the base? If hydroxide was the base, we would get what? This plus water. That's 25, 16. Which side's favored? This side. So is hydroxide going to take us to the other side? No. No, hydroxide will not do this. The more common hydroxide base is not strong enough to do this. You have to use stronger bases. Right? Which one's a stronger base? Well, obviously that one because we said it works. But why is that a stronger base than that? Why is that a stronger base than that?
Because it's a weaker acid. It's conjugate acid.
This is electron density.
Tell me more.
It has more electrons to run. So the H, because it has on OH, you only have one H on it, so you have less electron density on
That
it.
has nothing to do with the H's. Nothing to do with the H's. The big difference is it's a different atom. And thus, just so you know, we have talked about this many times. You should know it.
Oxygen.
It's not nothing new. So
Larger, so the electrons.
oxygen is larger. No, oxygen is actually smaller.
Nitrogen, yeah, okay, so what's the electrons?
It contracts as you go across. Oxygen is smaller. Oxygen is more electronegative and thus holds the electrons tighter. It's a better parent. It's not as eager to go take that H. It's holding the electrons tighter. It's more stable. The electrons are attracted more to the nucleus because the oxygen nucleus has one more proton than the nitrogen nucleus. But that's electronegativity. That's what electronegativity means, right? Okay? We talked about that. You should know that. Finally, there is a final exam in the course. All right, guys? Okay, this reaction does not take place. So actually, this reaction is favored. What is that? The acetylide anion will react with water to give what? To put the H back on. Yeah? That's what I'm showing here. Calcium carbide is actually the dianion of acetylene. C2. C2 is just this. What's the charge of the calcium? 2 plus. What's the charge of each of these carbons? Minus and minus. Now what happens if you put an acetylide anion in water?